Everyone. So in this class let me discuss limits and continuity. So here definition neighborhood of a point. So here let C be any real number if A and B are any two real numbers such that A is less than C is less than B, then the open interval A comma B is called neighborhood of C. So here a real line is there. Here 2 points A and B. Here A is less than C is less than B. Okay. So around C we make an open interval C. Then the open interval A comma B is called the neighborhood of C. Or in other words, let S is subset of R and A belongs to R. Then S is said to be neighborhood of A if there is an open interval I such that A belongs to I and I belongs to S, or if there is delta greater than 0 such that A minus delta comma A plus delta is subset of S. Okay. So here I take a real line from minus infinity to infinity. So here A is a point and that belongs to I. So here I draw an open interval I, okay, and A belonging to I. Okay. Later I construct S, closed interval S, and that here your I also belongs to S, because A is contained in I and S. Okay, and so this belongs to I and this belongs to S. So then this satisfies the definition of your neighborhood of A. Okay, so another for this, if delta greater than 0 such that A minus delta and A plus delta is subset of S. So for that diagrammatically, so consider a real line, draw a real line, okay, denote a point A. So construct an open interval from here to here A plus delta and here to here A minus delta. So whatever the distance from here to here is there, so you less that, so that is your delta is greater than 0, then you construct an open interval A minus delta to A plus delta. So that is subset of what? S. So here I can draw a closed interval S. So then your A minus delta and A plus delta is subset of what? S. Okay. So note here a note is there. So note real number line is neighborhood of all real numbers. Real number line is neighborhood of all real numbers. Next let me see symmetric neighborhood of C. If C is the midpoint between A and B, which is symmetric neighborhood, then the open interval A comma B is called symmetric neighborhood of C. So here construct draw a real line and denote a point C. So whatever the distance from C to B is there, so you point a point here that distance should be this from A to C and C to B distance should be same. Then we can say that is symmetric neighborhood of C. Symmetric neighborhood of C. So now the next definition is epsilon neighborhood of C. So if epsilon is a positive real number, then C minus epsilon comma C plus epsilon is symmetric neighborhood of C. Then it can be expressed as C minus epsilon is less than X is less than C plus epsilon, or modulus of X minus C is less than epsilon. So construct a real line and your C minus epsilon from a distance from C minus epsilon to X and X to C plus epsilon should be symmetric neighborhood of C. Okay, symmetric neighborhood of C. So this satisfies the definition of your epsilon neighborhood of C. So next deleted neighborhood. If from the neighborhood of a point the point itself is excluded or deleted, we get the deleted neighborhood of the point. So take a real line. Okay, so from around C, so we take an open interval A to B. So if C is deleted itself, then we get the deleted neighborhood of C. Okay, so bounded function. So here a function f of x defined in an open interval D is said to be bounded above if there exists a real number m such that f of x is less than or equal to m for all x belongs to D. for all x belongs to D. So this is bounded above definition. So next, a function f of x defined in an interval D is said to be bounded below if there is a real number m such that m is less than or equal to f of x for all x belongs to D. So you know the examples of these two is, so if I take n and your n belongs to n, then if you put the value of n in place of natural numbers, so if you put n is equal to 1, 1, n is equal to 2, 2, so you get a set of natural number set. So in that your bounded above point is, we can't say, so there we get, so if I take minus n, then here your 1 means value of n is minus n is minus 1, minus 2, minus 3, so on up to infinity. So here we get a bounded above point. So here we get a maximum point, that is minus 1. So minus 1 is the bounded above point. So in a set of natural number set, so here we get a bounded below point, but we won't get bounded above point. Okay, so a function f of x is said to be bounded in an interval D. It is bounded above as well as bounded below. Okay, so that is m is less than or equal to f of x is less than or equal to m for all x belongs to D. So for that example 1 by n, so if your n reaches towards infinity, so then your the value of that 1 by n value of 1 by n is towards 0. So if your n is equal to 1, so then you get 1. So it runs, so what value of that 1 by n is, so that is 0 is less than or equal to f of x is less than, if you take f of x is equal to 1 by n, then it lies between 0 and 1. So next, least upper bound a real number m is said to be least upper bound or supremum of f of x in an interval I if f of x is less than or equal to m for all x belongs to I and m is an upper bound. So for every epsilon greater than 0, there exists at least one element x naught belongs to I such that m minus epsilon is less than f of x naught, or for epsilon greater than 0, m minus epsilon is not an upper bound of f of x. So greatest lower bound, a real number m is said to be greatest lower bound or infimum of a function f of x in an interval I if m is less than or equal to f of x for all x belongs to I, and second condition is for every epsilon greater than 0, there exists at least one element x naught belongs to I such that f of x naught is less than m plus epsilon, or for epsilon greater than 0, m plus epsilon is not an lower bound of f of x. So next definition, monotonic function. So here a real valued function f of x defined in a set A is subset of R is said to be monotonically increasing if for x1 is less than x2. That implies that is f of x1 is less than or equal to f of x2 for all x1 x2 belongs to I. So if x1 is less than x2, strictly less than x2, so that implies that f of x1 is less than f of x2 for all x1 x2 belongs to A, then f of x is strictly monotonically increasing in A. So next definition, if for x1 is less than x2 and your function f of x1 is greater than equal to x2, f of x2 for all x1 x2 belongs to A, then f of x is said to be monotonically decreasing in A. So that implies if x1 is less than x2 and f of x1 is less than f of x2 for all x1 x2 belongs to A, then so here strictly inequality is there. So then the function f of x is said to be strictly monotonically decreasing in A. So definition of monotonic, so that is a function f of x is said to be monotonic if it is either monotonically increasing or monotonically decreasing in A. So here some important results are there. So those are algebra of limits with proofs. So here I am giving algebra of limits with proofs. So theorem, if limit extends to a f of x is equal to, so here before that we define limit of a function. So the definition of limit, a real number L is said to be left hand limit of f of x as x tends to a if for any arbitrary chosen epsilon greater than 0 there exists a corresponding delta greater than 0 such that f of x minus L is less than modulus of f of x minus L is less than epsilon whenever a minus delta is less than x is less than a. So that can be denoted as limit x tends to a f of x is equal to L. So this is left hand limit definition. So next definition is your right hand limit. A real number L is said to be right hand limit of f of x as x tends to a if for every epsilon greater than 0 there exists delta greater than 0 such that modulus of f of x minus L is less than epsilon whenever a is less than x is less than a plus delta. So limit x tends to a f of x is equal to L. So next definition is a real number L is said to be limit of f of x as x tends to a if for any arbitrary chosen epsilon greater than 0 there exists a corresponding number delta greater than 0 such that modulus of f of x minus L is less than epsilon whenever 0 is less than modulus of x minus a is less than delta. So we often use this definition to prove some of the theorems. So you remember this definition very carefully. Okay, so next result is, so that is a theorem, if limit extends to a f of x is equal to L and limit tends to infinity g of x is equal to m, then prove that limit n tends to infinity f of x plus g of x is equal to limit n tends to infinity f of x plus limit n tends to infinity g of x. So you know that limit n tends to infinity f of x is L and limit n tends to infinity g of x is equal to m. So we prove this result. So let epsilon greater than, so here I use the definition of your limit of a function. So here let epsilon greater than 0 be given since limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to m. So here there exists corresponding delta 1 greater than 0 and delta 2 greater than 0 such that modulus of f of x minus L is less than epsilon by 2 for 0 is less than modulus of x minus a is less than delta 1 and modulus of g of x minus m is less than epsilon by 2 for 0 is less than x minus a is less than delta 2. So for the definition of limit we use let epsilon greater than 0 be given. So here there exists corresponding delta greater than 0, then your modulus of f of x minus L is less than epsilon for 0 is less than modulus of x minus a is less than delta. But in the case of these two functions, here I am defining two functions with the definition of your limit of a sequence. So therefore here I am considering delta 1 is greater than 0 and delta 2 greater than 0. So therefore your definition becomes modulus of f of x minus L is less than epsilon by 2 for 0 is less than modulus of x minus a is less than delta 1 and modulus of g of x minus m is less than epsilon by 2 for 0 is less than modulus of x minus a is less than delta 2. So here I take if delta is minimum of delta 1 and delta 2. So minimum of delta 1 and delta 2 I take it as delta. So then clearly from equation 1 and 2 holds good for 0 is less than modulus of x minus a is less than delta. So minimum of these two value I take that as delta. So then your 0 is less than modulus of x minus a is less than delta becomes. So hence here I take modulus of f of x plus g of x minus L plus m is equal to modulus of f of x minus L plus modulus of g of plus. So this becomes f of x minus L and this becomes g of x minus m. So minus into plus is minus. So then it will become g of x minus m. So modulus of, you know that modulus of x plus y is less than or equal to what? Modulus of x plus modulus of y. So using that property I write it here. So this is less than or equal to modulus of f of x minus L plus modulus of g of x minus m. So you know that modulus of f of x minus L is less than what? Epsilon by 2, and modulus of g of x minus m is less than what? Epsilon by 2. For 0 is less than modulus of x minus a is less than delta. So half epsilon plus half epsilon, so you get here epsilon. So therefore again I use here the definition of limit point of a sequence, So then here apply here for this function I apply limit, so then it will become limit x tends to a f of x plus g of x is equal to you get here limit f of x as x tends to a and limit g of x as x tends to a. So you know the value of limit x tends to a f of x is L, and limit x tends to a g of x is what? M. So therefore using the definition of this, your result follows. So in the similar manner we try to prove this result, that is your if f of x limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to M, then prove that limit x tends to a f of x minus g of x is equal to limit x tends to a f of x minus limit x tends to a g of x. So that is L minus M. So let epsilon greater than 0 be given, since limit x tends to a f of x is equal to L and limit x tends to a g of x is equal to M. There exists corresponding delta 1 and delta 2 greater than 0, such that your f of x modulus of f of x minus L is less than epsilon by 2. For 0 is less than modulus of x minus a is less than delta 1, and the modulus of g of x minus m is less than epsilon by 2. For 0 is less than modulus of x minus a is less than delta 2. Take it as equation 1 and 2. So if delta is minimum of delta 1 and delta 2, then clearly from equation 1 and 2 hold good for 0 is less than x minus a is less than delta. So here I take modulus of f of x minus g of x minus L minus m. So then it will become, so f of x minus L, and this is minus, this is also, this become plus, minus into minus becomes plus. So if I take negative sign common, then it will become g of x minus m. So modulus of x plus y is less than or equal to what? Modulus of x plus modulus of y. So therefore I write this as modulus of f of x minus L plus modulus of g of x minus m. So you know that modulus of f of x minus L is less than epsilon by 2, g of x minus m is also less than epsilon by 2. So therefore here we get epsilon. For 0 is less than x minus modulus of x minus a is less than delta. So again we use the definition of limit of a limit. So then we get here limit x tends to a f of x minus g of x is equal to L minus m. So this is equal to limit f of x as x tends to a minus limit x tends to a g of x. So this is the result. So these are simple proofs. So you follow it. So if you have any questions regarding these concepts, you can send questions to my WhatsApp number and clarify your doubts. Thank you.